last time we discussed about formula about how the virtual cycle of a space, a moduli space that undergoes an action of a torus, localizes to the virtual cycle of the torus fixed locus part of that space. We need to modify, of course, these two cycles are not equal to each other, this one and this one. You need to modify the formula and you need to basically divide by Euler class of the normal bundle. Now, the reason it's called virtual normal bundle in here is that if the space is a smooth, for instance, torus fixed locus of certain moduli space is a smooth, then it will have a normal bundle. But often there is an object that lies on it that, other than just sections, will have higher cohomologies. So it's not going to be a locally free sheaf. There's an obstruction for it becoming locally free. And that obstruction makes it into something that if you take its cohomology, in K theory, for instance, it will have H0 part minus H1 part plus H2 part minus H3 part, so on and so forth. So here our normal bundle is also having higher cohomologies. It actually has two terms, deformation part and obstruction part. That's why we call it virtual normal bundle. It's not really a bundle. It's a combination of cohomology classes. And then how we recover it, we discussed that we are looking at by definition, in fact, all you need to do is look at the obstruction complex of the moduli space. That's a complex. And basically, it's an alternating sum of its cohomologies. But this normal bundle is the normal bundle to the torus fixed locus of the moduli space. So this object in the derived category, this E dot, senses the action of the torus and it decomposes. So this object, E dot, decomposes into E dot T fixed plus E dot T moving. So that means that this is the part of this complex which is not moving or changing at all by the action of the torus. And this is the one that actually does change and gets dilated. And the virtual normal bundle is actually the equivariant Euler class of the T moving part of E dot. Okay. All right. So let's now do some example and see whether we can actually show how to compute these kind of things. So some examples of torus equivariant localization of dt invariance for C3 and local P1. This is a local curve, Calabi-Yau threefold. It essentially means it's a piece that has a P1 in it, and a rank 2 bundle, O minus 1 and O minus 1, is supported on it. So the total space is actually a threefold. But locally, it looks like P1. Locally, it's compact. Globally, it's not compact. Okay. So both of these spaces are undergoing action of C star cubed. So C star is acting on here, and C star cubed is acting on this one too. The space is being acted by the torus, and therefore the moduli space also is getting acted by the torus. So let us see how to compute C star cubed fixed sheaves on these spaces. Okay, so let us assume Our moduli space. Moduli space is parameterizing ideal sheaves. Ideal sheaves of subschemes Z in X. X is either local P1 or C3. Okay, X is either local P1 or C3. Okay, so here is what we are doing. These are ideal sheaves. So given a monomial ideal I in the polynomial ring XYZ with complex coefficients corresponding to a zero-dimensional subscheme, we can consider the associated three-dimensional subscheme of X. We can consider the associated set of lattice points. Lattice points, which are, let's call this thing pi of I, the ideal sheaf. So I'm gonna tell you what this means is the set of A and B's and C's in Z3 such that XA, YB, ZC is not inside our ideal. This defines a three-dimensional partition function. I'm sure that you have heard of Young tableau diagrams. So let's do a toy example of I want to ambient variety X to be a two-dimensional space, let's say C square. This is X minus C square. C star square is acting on this X. Here, I'm going to, so O of X is locally as a module given by the polynomial ring in X and Y. And I would like to look at ideal sheaves of subschemes inside this X, which are given by monomials. So this is essentially sitting in here. And then the co-kernel of this thing is the structure sheaf of that subscheme. Pick a monomial. Let us pick a monomial. So let us say locally, I of Z inside X is given by this monomial ideal. So let's say X squared Y, for instance. Okay. So how do we get a combinatorial object that understands this ideal? So we were trying to come up with a combinatorial diagram of or object that basically represents this ideal. It's actually very easy. Locally X is C squared. So C squared has two axes, the x-axis and the y-axis. And there is a torus acting on X and there is a torus acting on Y, right? So what we can do, we can construct an integer lattice, on C squared, basically. So let's say this point represents X to the 0 and Y to the 0. This point, which is in the X direction, let's say it represents X to the 1. This point represents X squared. This point represents X cubed, and so on and so forth. This point represents Y to the 1. This point represents Y squared. This point represents Y cubed, so on and so forth. Now, if you have mixed, if I have something like X, Y, and I would like to see where is that. That is basically 1 power of x, 1 power of y, and this is exactly going to be x times x to the 1 times y to the 1. If I have x squared times y, I will come 2 degrees onto the right, and I will go 1 shifted up, and this is going to be x squared y, so on and so forth. Okay, so this is clear, right? Any questions? All right. Now, the very property, so let's pick that ideal, x squared to the y. You see, the very property of ideal is that this is something that it's a module that sits inside the polynomial ring. In particular, any combinations of x and y's that get multiplied by these generator of this ideal are also going to be inside this ideal. So for instance, this ideal as a set, of course, has x squared times y, but if I keep multiplying it by x, so x cubed y is also there, x to the 4th y is also there, all of them are there. If I multiply it by y, x squared y squared is there, x squared y cubed is there, and so on. If I multiply it by any whatsoever polynomial inside this ring, all of those are going to be there. All right, so as you can see, if I actually locate x squared y, then I can immediately see that anything, so I can draw a line in here, anything that I multiply this with above this line and on to the right hand side of this line is going to be inside this ideal, right? So basically, this is what it is. Now, if I have some other thing, some ideal, my ideal has a generator that has x squared y, and for instance, I don't know, x y squared is generated by 2. All I need to do is to find where that lattice point is in here. This is exactly xy squared, and anything on the right hand side of this thing, why? Because if I keep multiplying this by y's, all of them are going to be there. If I keep multiplying it by x, all of them are going to be there. So as you can see, this is also there. Okay, good. If I have a generator, which is, for instance, over here, and it has x cubed, that's x cubed right there. And then anything to the right hand of x cubed and anything to the top part of x cubed, meaning all combinations of x cubed times y, x cubed times y squared, so on and so forth, are also going to be there. So as you can see, eventually, when I look at the ideal, I can separate the part which is not inside my ideal. So, all right, so I need to have something like y to the 4th, for instance. Let's just say y to the 4th is here, anything in here and anything in here is also going to be there. So in fact, the picture tells you that you can find generators, you can put generators inside this ideal in a way that the part of the picture which is not inside the ideal becomes finitely many number of boxes. You see, these are boxes, these are boxes. Right? Something like that. And as you can see, by looking at this ideal, which sits inside the polynomial ring of x and y, we can see that there is a one-to-one correspondence between this ideal, which separates all the pieces that are not in it, from the ambient unbounded part of the space. So in fact, if someone asks you, you have this Z2 lattice, integer lattice, and of course powers of x can also become negative, there's no problem, and so on. If it is a Laurent polynomial, but here we are looking at only positive degree. So if you have that, then essentially ideal is not just the generator, but everything that gets multiplied to that generator is also ideal. So this is basically ideal of this subscheme of X. And this ambient space, this whole positive side, the first quadrant of the two-dimensional space, is essentially just C squared, or C of X and Y, because it has all positive degrees of X and Y in it. And okay, and as we can see, this infinite thing sits inside this finite thing, so it gets injected inside it, and there is something that captures the discrepancy between the two, and that must be the structure sheaf of the subvariety itself. So this part is actually the module that corresponds to O of Z. Okay, so having a very simple calculus, you can actually see that you obtain this nice, beautiful combinatorial picture associated to some subscheme of the ambient variety that sits inside C2. Okay. Now, I would like to ask you, Mohammed, a question. What's the dimension of Z?
Trying to get it from the ideal generated by it.
No. What's the dimension of it? It's a subscheme. Ambient space is two-dimensional, right?
Yes.
You have a finite box configuration associated to Z, O of Z, and the ideal, now you know what it is. What do you think is the dimension of this subspace or subscheme Z that sits inside C2?
Well, not sure.
Okay, let's look at it. Well, if it is, let's look at the C2 again. And this is my integer lattice. Let's look at the x-axis in C2. X-axis in C2 and the functions defined on the x-axis are the things that have x in them, right? So the polynomial ring of x-axis was only C of x. So basically this box is there, this is there, this is there. All of them are here, right?
Yeah.
Okay, it goes forever. And y-axis also is the same thing. So this is the y-axis. This is the x-axis, and this is the y-axis. So as you can see, x-axis and y-axis are combinations of union of boxes which capture the degree of x's that you can have in there, and they are just unbounded. So when you look at this picture, I say, what is the dimension of Z? You look at the part which is associated to structure sheaf of Z, and this is this.
Yeah.
And you can see that it's a bounded object. The only way that you can have finitely many boxes representing Z is that dimension of Z is actually equal to 0. Because if Z is one-dimensional, it should go to infinity, right? Its polynomial ring should have infinitely many degrees of one of the variables or the combinations of, right?
Yeah. Yes.
So if dimension of Z is bigger than or equal to 1, then we have infinite boxes. Infinite boxes, exactly, representing O structure sheaf of Z. As soon as you see that this Z is actually not infinitely many boxes, the structure sheaf of it, ideal sheaf of it has all of these boxes, because that's exactly what the ideal sheaf is about. But the structure sheaf is actually determining what it looks like. So a structure module of this subscheme is actually finite combination of these boxes. So that tells you that seems like Z is some kind of a point. And it's a fat point, you see. So this picture combinatorially even tells you that if inside X and Y, this ring, I pick generators X squared, Y, XY squared, X cubed, and Y to the fourth, the module that it gives me, which is C of XY, divided by the ideal X squared Y, comma, XY squared, and then X cubed, and then Y to the fourth. This thing would be actually a skyscraper sheaf of a point, of a fat point. And why do I say fat point? Well, if it's a point on the x-axis, let's say X, I can have X squared on it, and that's a fat point, right? So this point also in here in this picture has a profile, and the profile of it is given by this finite box configuration here. Doesn't need to be always just X or Y. It could have X and Y or combinations of those. So this is the profile of fat point Z that sits inside C squared. Okay, so did you learn this interesting game?
Yes, now I see it. Yeah.
Perfect. So as soon as you fix an ideal inside ambient polynomial ring, that ideal choice of that ideal in the kind of situation where the polynomial ring is being acted by the torus gives you a Z lattice, integer lattice, or Z square lattice, or Z cube lattice, depending on what's the dimension of the ambient space is. And this Z integer lattice is integer lattice because this is actually decomposition of the ambient C square, for instance, here, or C cubed, or whatever the space is, into a polytope, on which the lattice points are basically capturing the character or weight of action of torus on them. Torus is acting on X, so if it is just one power of X, it just gets dilated by T times the torus. But if it is X squared, if I modify X to Tx, then X squared will give me T squared X squared. So that means it's weight 2, because the power of T gives me the weight of the action. So this is the weight 1 part, the weight 1 lattice point, and this is the weight 2 lattice point, weight 3 lattice point. In the Y direction, weight 1 lattice point, weight 2 lattice point, so on and so forth. So this integer lattice that you have in here, all of these together are actually capturing the weighted space that C2 induces because of the action of C star square. Okay, so this is nice because, as you can see, if I asked you how many, for instance, how many certain, and by the way, number of these boxes here, number in the previous example, let me write it down. In the previous example, sorry, let me actually do this thing because this is going to bother us. Okay, so in the previous example, number of boxes tells us about multiplicity. of the point. So it's a fat point of whatever multiplicity it is. You need to count how many boxes you have here. 1, 2, 3, 4, 5, 6, 7. For instance, multiplicity 7. And the other thing about this is that, so, okay, so this is interesting. And then the other thing is that you can play games now. So how many points of multiplicity 7 could we have, for instance, in C2? Well, essentially, that means that on this very corner of the x-axis, you need to basically tell me how many box configurations of length 7 can you have. You can put them, all of them like this, 1, 2 to 7. You can put them all like this, 1, 2 to 7. You see, you can do counting problem. You can do this kind of configurations. You can do this kind of configurations. It's box counting problem. As soon as I fix the length of the zero-dimensional subscheme in C2, or the profile of it, you can basically say now that it's just boiled down to combinatorics problem. I can just count how many box configurations I have. And that gives me the possible number of points I can have. Now, one thing is that this is torus fixed point, actually, because essentially, if you look at it, it's all supported on the origin, which is inside C squared. And the origin of C squared is the only torus fixed point of C squared. Anything else inside C squared, by the action and dilation of torus, moves around. If I pick a point in here and I act on it by torus, it moves around because it's a weighted space, and these lattice point gives me where the point is based on the weight of the torus that acts on it. Okay, but the origin doesn't. So any finite box configuration which is supported on the origin, meaning it's in the very corner of this diagram, is actually a torus fixed point of C2, you see? So we already are counting sheaves in a very nice way without really even doing anything. We are counting torus fixed sheaves, meaning their support needs to be on the origin because the origin is the only place that we can have such a thing. But we allow some kind of nilpotent fattening of origin, both in the X and Y direction, which actually means that we can get some two-dimensional finite box configuration like this. So anything cornered like this is reminiscent of a torus fixed point inside C2. So this was a beautiful thing. And I think one of the people who taught mathematics community of this representation is actually Andrei Okunkov. And this method actually kind of has roots in statistical mechanics and physics. It's called melting crystal diagram. If you have a cup of coffee like this, and you put a lump of sugar in it, and you dip it inside like this, after you turn it, take it out, it will have some part of it melted. This is exactly the part which was melted out. And the rest of the lump of sugar is here. That's why this box configuration methodology to represent torus fixed points or torus fixed subschemes or subspaces of an ambient space that undergoes an action of a torus is called melting crystal configuration. All right, any questions, Mohammed?
No.
All right, have you seen this melting crystal?
No, but I have seen some Young
People.
diagrams. And yeah, I know Uncle Kunkov, yeah, he did some stuff like this. I remember reading some of these stuff, or instantons, for example.
Perfect. Yeah, exactly. So let's put everything I said in the in writing also. So okay, so this I mentioned. Recall that now. Okay, so all right, so we obtain a melting crystal diagram associated to zero-dimensional subschemes Z in C squared of fixed length. Length mean how many boxes. So length, this is length 7. This is also length 7. This might also be length 7. Okay, so a fixed length in subscheme Z of fixed length, like this. Okay. All right, so counting these box diagrams or these Young tableau diagrams actually tells us about counting of sheaves, which are being generated, which are actually fixed in some sense, torus invariant or torus equivariant via the action of the torus. Okay, so now how can we use this in actual calculations? So recall that deformation obstruction theory of moduli space is of ideal sheaves is given by a map in the derived category from E dot to L dot of I chi x beta moduli space of ideal sheaves, where the underlying ideal sheaf has curve class beta and Euler characteristic chi, where HI of the dual of the obstruction, deformation obstruction complex, are given by, for I equal to 0 and 1, only two non-vanishing cohomologies are given by X1, ideal sheaf of Z in X, comma, ideal sheaf of Z in X. These are the sheaves we are parameterizing. And X2, trace free, ideal sheaf of Z in X, comma, ideal sheaf of Z in X. X1 and X2. Therefore, when you do calculations, therefore, we can find a combinatorial, it's called T representation or torus representation, C star, I mean, T here means torus representation of E dot as follows. Okay, if you look at K group, this is the Grothendieck group. In Grothendieck group or in the K theory, E dot is actually given by the difference of its cohomologies. So it's the class, this is the class in K theory of its first non-vanishing cohomology minus its second non-vanishing. Okay. So if that's the case, if we are looking at the situation that torus is acting, you can just replace K theory with equivariant K theory. We can, in case of toric varieties, or in case where T acts on the moduli space, we can consider torus equivariant K theory. Okay, everything would be torus equivariant. Polynomials would be polynomials which are torus equivariant. Invariant really means that your polynomial is not changing by an action of a torus. Equivariant means it gets scaled by some factor of t. That's what it means, torus equivariant versus torus invariant. Okay. So for instance, in C of xy, the only torus invariant polynomial is constant because it doesn't have any x and y. X and y are both being dilated by C star. But torus equivariant polynomial, all the monomials are like that. So for instance, x squared is like that. Because if I change x with t times x, action of C star squared on C squared is given by, for instance, let's say t acting on x and y being tx and ty, for instance, action of C squared for now, for the time being, this one-dimensional torus. Okay, so if I change x with tx, this would be t squared x squared, and it's dilated, but that's the worst thing that can happen. If there's a non-homogeneous polynomial, then this will be t squared x squared plus t cubed y cubed. It's not equal to some factor of t times purely the original polynomial. It's not like that because the powers are different. But if it is something like x times y, then it is equivariant because this is going to be ty times tx, and I can write it as t squared times original polynomial. And it becomes equivariant again. So this is what equivariance means. Okay. So in equivariant K theory, we can look at the K group associated to the obstruction complex. And now suppose that virtual dimension, which we discussed, of I of chi x beta, this moduli space is equal to 0, then the dt invariant of this moduli space was given by integral of 1 against the virtual class. But now I can actually use the localization formula that I had before. I can say that this moduli space, I can replace I with torus fixed locus of I and replace this over there. So I can say that this will be an integral of 1 over equivariant Euler class of the virtual normal bundle, summing over I chi x beta virtual t fixed part of it. So basically, I can just put t in here, meaning t fixed part. And I can add over t fixed components. Okay, and then I know what the equivariant Euler class of this thing is. This is going to be the equivariant Euler class of the K-theory group of XI, because the virtual normal bundle, by the way, is just the difference of cohomologies of E dot. Equivariantly, E dot, the class of E dot in K-theory, is exactly equal to the virtual normal bundle. That's what it means, difference of classes. So you can just basically put this right there. I, okay, the K-theory, T equivariant, K class of it minus X2 II 0 TK theory. Okay, and then basically, if you take the Euler class of difference of two things, it's basically going to be Euler class of the first term divided by Euler class of the second term. This is basically part of some part calculus of Euler class. Differences become divisions, like that. So this is going to be summing over all ideals Z in X, which are part of the moduli space, points in the moduli space, but not the whole thing, but the T fixed locus of it, of E of T. So this goes to the numerator because it's 1 divided by that. So this is X2 I divided by ET X1 I. So this is basically that calculation. Okay. Mohammed, any question?
No, everything seems okay.
Exactly. That's right. This is the example of the zero-dimensional instantons. This box configuration represents a zero-dimensional.
Okay, yeah. Now I see the connection.
Yeah. So that's ideal sheaf I comma I, this thing. This ideal sheaf is basically this, the rest of the diagram. And this is C in here, CXY modulo that ideal sheaf. That's the structure sheaf of Z. This finite box configuration, okay? All right, so it's like that. And then now, if you look at the example, so here's an example. If ideal of us Z in X is given by the ideal generated by X and Y and Z, then one can see that the C star cubed character of N virtual normal bundle is above, basically, becomes the following thing. Becomes something like, so there is C cubed and there is C star cubed acting on it. What is C star cubed? That is T1, T2, T3, all non-zero complex numbers acting on X, Y, Z. And the action is given by T1 times X, T2 times Y, T3 times Z. That's what the action is. And basically, you need to derive from here some polynomial or some expression in T1, T2, T3. And this should be some expression in T1, T2, T3. So this should be some expression in that. And this should be some expression in that. Think about vector bundles. If I have a vector bundle, which actually is equivariant with respect to action of a torus, what does that mean? It means that I can look at this. I have a vector bundle V, vector bundle. Okay. Fiber of this vector bundle on a point, let's say we look at. So fiber of vector bundle at a point. If the vector bundle is two-dimensional, for instance, rank 2, the fiber of it over that point is a two-dimensional vector space. Now, if it is an equivariant vector bundle, I can act by some torus on this point P, and I can move the point P to here, T times P. Then I would like to see what is the difference between V of TP, right? How the V and V over P and V of TP are different. The fact is that because it's a vector bundle, its fibers over these 2 points are flatly changing. So as vector spaces, this vector space should be isomorphic to this vector space. Now I have honest to God vectors. And I'm saying they are same. So there is a map which is an isomorphism from one to the other. And of course, this map is given by a matrix, because it's a linear map between the two. So the trace of this matrix, or the character of this matrix, the character is basically given by the trace. I can calculate the trace of this matrix. And that's a polynomial in T. Okay, so each time you give me a vector bundle, I can calculate if the underlying space of this vector bundle is undergoing an action of a torus. I can calculate character of action of T on that vector via pullback. Why is it pullback? Because P has changed to T times P, and I'm looking at V, P, and I'm modifying this by looking at T times P. So it's like I'm pulling it back via the action of T. So this is how the action is induced on the vector bundle. Now I have an object which is not vector bundles, but it's sheaves. So this object is E dot. It has two cohomology sheaves. It's H0, E dot dual, for instance, is a sheaf X10 I, comma I, and its H1 is a sheaf X20 I, comma I. But sheaves are kind of also similar to vector bundles. So I can calculate T character of this guy, T, the torus character of this guy, and I can calculate the torus character of this guy. Yes, and if I do that, then the torus character of one divided by the other can be calculated. And these are basically those representations, or the T representations that we are talking about. So what is the matrix that gives you homogeneity of this sheaf as the base of the sheaf moves from one point P to T times P, and the other one as well? So calculate the T characters and you subtract them from each other in K theory. So those are what those T representations are. And in a particular example where ambient space is C cubed, and I have, I'm calculating character under the action of C star cubed, the equivariant character, the character of the Euler class of the virtual normal bundle actually becomes something like this: e to the T1 plus e to the T2 plus e to the T3 minus e to the T2 plus T3 minus e to the T1 plus T3 minus e to the T1 plus T2. And you should really think about this as infinite series, because you're looking at these things in terms of their Taylor expansion. So 1 plus T1 is square plus blah, 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 plus 1 plus T2 is square plus blah, 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 so on and so forth. Okay. So for more detailed computations of T character of virtual normal bundle, on I chi x beta, look at MNOP paper, Donaldson-Thomas and Gromov-Witten theory. This famous paper where they conjectured that Donaldson-Thomas and Gromov-Witten partition functions are related to each other. Okay. So, all right. So this is how we do this calculation. And after calculating equivariantly, after computing the integral t equivariantly, we obtain a series, an infinite series for dt invariants in terms of characters t1, t2, and t3. For instance, in this example, c cubed, we get partition function of dt invariance because summing over Euler characteristic of this times q to the chi. This is exactly integral of 1 against the virtual cycle. This is our invariant. And that actually becomes equivariantly because as soon as you replace the virtual cycle by the torus equivariant or virtual cycle of the torus fixed point, everything will see the action of torus and everything becomes an equivariant thing and a description in terms of the torus. So it becomes something like summing over all partitions, finite box configurations, T1 plus T2, T1 plus T3 times T2 plus T3 divided by T1, T2, T3. Some calculation like this. Q to the particular, let's call this box configuration pi. Q to the particular power pi. And this is exactly the description, this infinite series. Actually, this is an infinite series. The Taylor expansion, if you write down the Taylor expansion of this thing, you can calculate what it is, and it will be an infinite series, and it's actually going to be exactly the McMahon function again. T1 plus T2, T1 plus T3, T2 plus T3, divided by T1, T2, T3, where M of Q is McMahon function invariable Q. Okay, any questions? Do you have any questions?
No.
I have some question for you. Let's say I give you, so I claim that right now it might be mysterious for you how we are obtaining a description like this. So I give you an example. Let's say our moduli space is Hilbert scheme of points in C2. Hilbert scheme of points. So there is no curve class. So C2 is given here. Curve class is equal to 0. But Euler characteristic of my sheaf, so I of z goes to O of x, goes to O of z. And I would like the Euler characteristic of O of z to be equal to n. And I would like homology class of z to be point class. So beta is equal to 0, actually. So this is Hilbert scheme of points. N points in C2. Okay, we would like to use this formula. there are so many ways that on C2 we can find configurations of points. But the whole point of this thing is that the virtual cycle of this moduli space via a certain formula can be actually localized to summing over all T fixed components of Hilbert's scheme of virtual cycle of the T fixed component of the Hilbert scheme divided by a covariant Euler class of the virtual normal bundled with Hilbert scheme. So let us look at the Hilbert scheme, T fixed part. T fixed part parameterizes T equivariant sheaves representing zero-dimensional subschemes in C2. Okay, so this is something that we just studied, right? The structure sheaf of these things looks like finite box configuration. Do you agree?
Yes.
Good. Okay, so those T fixed parts are all finite boxes. So these are exactly finite box configurations. And you might say, how finite are they? Well, the thing is that it has to do with the length. You need to fix the length. So we are fixing the Hilbert scheme and the length of these boxes to be n. So basically, I'm looking at all the possibilities when number of boxes as a whole is going to be n boxes for me. Now, I ask you a question. If I give you a box configuration like this, 2 in here and 1 in here. This is x and this is y. Okay, and C star square is acting on C square by T1, T2 acting on x and y, T1 times x, T2 times y. What is T character of, this is my O of z, of O of z? What do you think?
So we don't have to go to the X groups. Just from the graph we can get it.
From the graph you can get it, but let's not even worry about the X group. Just okay. O of z itself. It's basically looking at this as a T representation. It's basically looking at it, asking yourself, what are the powers of T that represents this picture? Here I have, here there is T1 0 and T2 equal to 0. And then this one is y and y squared. This is x and x squared, right? Yeah. So you can basically say that so it is generated by you. All you need to do is basically to write it down as.
So I look at the corner points then?
Exactly. Exactly. So it is T1 0 to T2 0 plus T1 to the 1, T2 to 0. This is this point plus exactly T1 squared, T2 0. That's that point. And then you need to write it like that. So it's going to be x squared times y. So T1 squared times T2. Then there is x times y there. And then there is y squared x there. And then there is y square
Y square.
alone there.
Okay.
You see? Do you
Yeah.
see how beautiful this is? The T representation
simple.
of this box configuration is basically something like this.
So a whole complex problem is now reduced to counting the
The T
characters of some
representation.
box configurations. Yeah.
Exactly. The whole thing is to reduce to this kind of thing. So if I had some situation where I had something like this, and this kept going, x-axis, then I would like to write down this T representation. So there is no power of y. So you look at left corner pieces. So y0, x0, y0x, y0x squared, y0x cubed, y0, it keeps going, right? y0x0 is 1 plus t1 plus t squared plus t1 squared plus t2 t1 cubed plus t1 to the fourth. It's just t1, right?
Yeah.
It's the x-axis. Do you agree?
Yes.
Okay, one-dimensional. It goes for infinity, right? The T representation also captures that, because the T representation is not going to be a polynomial, but it's going to be a power series. Right? And it is exactly this power series. And what is this power series? This is the Taylor expansion of 1 over 1 minus T1. Do you agree?
Yeah. Yeah.
There you go. You see? So this is how this calculation is done. When you look at the box configurations, the T representation captures what the box configuration gives you, but in terms of weights of the action of the torus on that space. So similar to the way that, so this is actually T character. If someone asks me what this is, I'm saying this is C star squared character of structure sheaf of x-axis, which is exactly module theoretically polynomial ring in the power in the variable x. Okay. So the same way that modules have this T representation, bundles also have T representation. Same way that the sheaf itself has T representation. If I have something like this, this also has a T representation. And this also gives me some description in terms of T1 and T2. Similar thing for X2. And I would calculate those things, and I would think of them as infinite series in terms of T1 and T2, but then via the Taylor expansion, it can be simplified to some expression like this. Okay. All right, any questions? Any questions here?
No.
Good.
That's very clear. Sure.
Very good, very good. Okay, so yeah, this is kind of the very heart of this, really. And this is the more important part. I mean, one thing about enumerative geometry is that there is intuition behind the concepts, which is really beautiful. And many experts have created these amazing things. But then there is computation. And the computation in this actually field is more important. Like if you cannot compute, essentially it's useless, basically. So learning this calculus and obtaining expressions and so on is eventually very important. I was at some point myself forced to learn the computation to the extent I needed. But there's plenty of papers on this thing and you can see examples. Okay, so that's that. Right. Now, let's look at this formula. We obtain this m of minus q to t1 plus t2, t1 plus t3, t2 plus t3. divided by T2, T2, T3. This is the partition function of dt invariance. Okay, some expression in terms of T. Okay, remark. We can simplify. We can simplify the formula obtained above by considering not the C star cubed action, but the Calabi-Yau, I'm going to call it a Calabi-Yau torus. Calabi-Yau torus is an expression T, which is a subtorus of C star cubed. Action on C3. What's the Calabi-Yau torus? By definition, Calabi-Yau torus is a subtorus of C star cubed, which fixes the volume form on X. So volume form is given by dx wedge dy wedge dz, and each one of these things have a character. This gets dilated by T1, this gets dilated by T2, and this gets dilated by T3. So the torus, which is a subtorus of C star cubed, which fixes the Calabi-Yau volume form, which fixes, it's called Calabi-Yau volume form, but anyway, which fixes the volume form, is given by combinations of T1, T2, T3, such that the weight of this object as a whole, after being dilated by the action of T1, T2, T3, is going to be not changing. That means the character of it, T1 plus T2 plus T3, right? Because if it is X, Y, Z, each one of them gets multiplied by T1, T2, T3. The character will be T1 plus T2, T3. This needs to be equal to 0, meaning as a weighted object, weight of it as a whole, we want to be 0. There is some sub-combinations of possible T1, T2, T3s. So in particular, if this happens, then this is what the Calabi-Yau torus is. And if this happens, that means that T1 plus T2 is minus T3, for instance. And T1 plus T3 is minus T2. And T1, T2 plus T3 is minus T1. If you do that, then you apply this in here, then you will see that the McMahon function under the action of the Calabi-Yau torus becomes the partition function under the action of Calabi-Yau torus becomes McMahon function to the power minus T2 minus T3, minus T3 minus T1 divided by T1 plus T2 plus T3. And then it becomes minus 1. And this is exactly what we had before. Where is it? We calculated one of these and we had this McMahon function. So where is it? There you go. You see? That's exactly what it is. Okay. So to the power 1, right? So we see that torus equivariant calculation or torus fixed calculation actually helped us to obtain first the T character of the deformation obstruction complex, then integrated over moduli space, meaning add over all possible configurations of boxes that represent points in the moduli space. Those are, for us at least here, finite length box configurations concentrated at the corner of C2. That's the melting crystal diagram. And then after adding, we got some nice formula, but this formula had T representations and T characters is still in it. And that's of course no problem because we are doing equivariant calculation. It will be an expression in T1, T2, T3. But under this constraint, then it becomes exactly the calculation we had before. Okay, any questions? All right, so this was one of the examples of DT localization theory. Next time we do relative DT theory and degenerations of DT moduli spaces. This is some technology that has been developed by Jun Lee and Baosen Wu. Using localization, you can calculate these partition functions over toric varieties, the way that you just saw. Now let us suppose that we have some X that there is no torus acting on it. So there is no torus acting on it. The idea is to degenerate X to some two varieties, let's say Y1 and Y2, that maybe they have some actions of torus, and do the calculation using torus localization there, which we very, very briefly touched on. And then if you can calculate partition function in here, you would like to be able to kind of relate it to original partition function of X before degenerating X. This is basically the story that we are going to talk about next time. Okay. So any questions?
No.
Let me go to the Zoom environment. Okay, what do you think?
That was some nice calculations over there. Yeah, like bringing something as abstract as moduli space of sheaves into something computational like this, using simple stuff like the box configurations, Young Tableau. That's really some powerful stuff.
It's a very, very powerful. Exactly, it's very, very powerful, and this is essentially how people compute. Eventually, if you understand the calculus of this thing, you can compute it eventually very easily. Identification of the torus fixed loci of these moduli spaces is the hard part. This example that we mentioned, Hilbert scheme of points in C2, is a very simple example. The only torus fixed point of C2 is the origin. If I have points roaming inside C2, the fixed points are going to be concentrated on the origin. It's not necessarily just the origin itself, could be fattening of origin in both directions.
Yeah.
So at least on C2, it's a Young Tableau diagram with the melting crystal concentrated in the corner. But that's not always your moduli space. Your moduli space could be P2. If it is P2, for instance, then, wait, did I lose you?
No, just there's the picture, but I heard you perfectly.
Mm-hmm. If it is P2, then torus fixed points in P2 are 3 of them. Because P2 has 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, right? Then counting points in P2, means counting torus fixed points in P2, dividing by equivariant Euler class, which is eventually some T character of virtual normal bundle, right? Okay, but over where? Over the 3 points. So if you are counting points of length n, multiplicity n, you cannot distribute n any way you want. 2 of them going there, 3 of them going here, n minus 5 of them going over there, or all possible. You see how interesting it is? Then you can count how many of them over there, how many of them over this point, how many of them over that point, and the product of them, all the counting partition, counting all box configurations of length L1, L2, L3 will be product Z of L1 times Z of L2 times Z of L3 times L1 plus, such that L1 plus L2, L3 is equal to N. So on and so forth. If you're counting curves, it becomes harder. If you're counting curves, then on P2, torus fixed curves, well, are things that are at least supported on the torus fixed lines of P2. And P2 looks like a triangle. Basically, write down the 3 vertices of P2, which are torus fixed points, and the lines connecting them are torus fixed lines. So every curve that is set theoretically supported on these things will be torus fixed, but it can deform a little bit. You see, now you have a notion of a fat profile, but not for a point configuration, but for a curve configuration.
Okay.
So if I have some curve configuration like this, let's say one of the fixed lines in P2, then this curve might be a fat curve. So I need to look at it as its cross section, and in the cross section I will see some profile, and that's a box configuration.
Okay.
You see?
Wow.
This is basically what is happening. So actually, let me show you. So because I want you to learn this calculus of it. So if I have these 3 locally, I have x-axis and y-axis and z-axis. Okay, so if I have that and I have a curve which is supported on the x-axis, right?
Okay, I can't see things. Did you share the screen?
Oh, sorry. Okay. You're right. You're seeing my kind of, sorry.
The blankness.
So there you go. So if you're looking at some curve configuration where the curve is supported on the x-axis, right? It is some kind of it could be a curve supported in here, but it could have some profile. It could be a curve with some profile, right? I could look at this profile, this cross section in here, and I can zoom in. And what do I see? I will see fattening of a curve that is supported on the x-axis, but the fattening itself in the z and y direction. So here I will locally see z-axis, and I will see y-axis, and I will see some kind of configuration like this. Okay.
So I can reduce the problem to another 2D configurations like
exactly. So then here you look at this cross section, you will see the y-axis, and you will see the x-axis, and you will see another profile. And over here, you will look at this cross section, and then you will look at here z-axis and the x-axis, and you will look at another profile. So essentially, your curve can be supported on the union of these things, because each one of these things are torus fixed. You can even have a curve like that. And therefore, now you need to basically look at all possible ways that a curve can be supported on either of these things, and all possible cross sections it can have along these axes. Okay.
So for each one of these, we do this for all kind of configurations, provided that the length is fixed.
Exactly. And now here is the other thing, which is also very interesting. From this calculus and this combinatorial representation, we have learned many things. We just did this example that if I have something along the x-axis, it's a power series. It's a power series basically in the variable t1, right?
Yeah.
All right. So if I'm looking at the curve configuration here, immediately I can basically, let's call this part of the curve the branch 1. and this is called branch 2, B2, and this is called branch 3. If I look at locally at branch 1, structure sheaf of branch 1, I know what to expect. It will be 1 over 1 minus T1, right? Because it elongates along the x-axis with many powers of T1 times a polynomial with finite degree in the other two variables, because on this direction, it's a finite intersection. It has a finite cross section, right?
Yeah.
And this one will be 1 minus 1 T2 times a polynomial of T1 and T3. And this will be 1 over 1 minus T3 times a polynomial, let's call it something else, FGE of T1 and T2. You see how nice it is?
Yes.
So the structure sheaf of this thing would be the representations, and basically would be adding these things. Okay.
Okay.
And this is very, 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 very cool, because you would eventually, reduce everything into combinatorics. And combinatorics is something nice that we can do, right?
Yep.
Perfect.
And then we can do, so this is like doing computations in C3, for example.
Exactly.
Okay. And even for higher dimensional, like complex spaces, we can do this and keep out projecting until we do.
Exactly. So if your variety is toric, you look at this original, this is called the polytope. You look at the polytope of your variety, which basically gives you a nice way of a stratified, where a hierarchical structure of what are the zero-dimensional fixed points of the variety, what are the one-dimensional fixed lines, one of the two-dimensional simplices, fixed simplices, and so on. And if you are counting sheaves, you want to count torus equivariant ones, their support needs to be on the fixed loci of this variety. So as soon as you use this fact, you can count them by looking at all possibilities. Sometimes counting is hard because counting partition functions is hard. But that's something that many people, strong people, have worked on. For instance, counting young tableau diagrams with fixed length is one of the expertise of number theorists like Professor Zagier. Don Zagier, for instance, has written plenty of papers on these things. There's plenty of research on this. It's a very sophisticated field on its own. So you actually can reduce the calculation to such instances and then do the calculation.